Hi, good morning. We discussed the gas laws previously, and basically, having gone through all of the equations, we need to do some examples so you can see how to apply the equations and which ones to apply. So first, let's take a look at something like this problem. Okay, you have a fixed quantity of gas. You have a gas. When we say fixed quantity, that means that N, the number of moles, is going to be held a constant. Okay, and this gas exhibits a pressure of 750 torr. It's at 21 degrees Celsius, and it occupies a volume of 5.12 liters. So what we want to do is determine the pressure, the volume if we increase the pressure. If the pressure is increased to 1.88 atmospheres, and the temperature to 25 degrees Celsius. Okay, so how do we approach this? We know we're holding N constant, but what we see is we have a pressure, my initial pressure, we have an initial temperature, and we have an initial volume. We're trying to determine the volume, and we had a change in pressure, and we had a change in temperature. So because I have all 6 variables, what we're going to need is the combined gas law. Okay, so this is how we determine what laws to use. Okay, so now that we do that, let's go ahead and fill in our values. Well, we know that P1 is 750 torr, but P2 is in atmospheres. So we need to convert, and we'll go ahead and erase this down here. So the first thing we need to do is convert. Let's go ahead and try converting atmospheres to torr. So we know that for P2, it's 1.88 atmospheres, and we know there are 760 torr in 1 atmosphere. Oop, I did it upside down, didn't I? That's not converting to torr. My units would have been atmospheres squared divided by torr. What kind of units is that? So make sure you keep an eye on your units, since they help you to determine whether you set up the question correctly. Okay? And when you do this, you get some value like, how about 1,428.8 torr, and we know it's going to be in 3 significant figures. Okay, so I'll put that up here. All right, so 1,429 torr, we want it to be 3 significant figures. Okay, then temperature, since we're working for gases, must always be in Kelvin. So we're going to add 273 to both our temperatures. So our temperature for T2 is going to be 298.15 Kelvin. Our temperature for T1, if I add 273.15 with, let me give you a different color. It would be 294.15 Kelvin. Okay? And our volume's in liters. Now, why didn't I do atmospheres? If you look at the form of your equation that you're going to use, these units will cancel out. If we were using the ideal gas law, then I would certainly change it from torr to atmosphere, because my ideal gas constant, R, is in liter atmospheres. Okay, so let's go ahead and use this formula now that we have everything. Okay, again, we're looking for V2. Okay, so we know that P1 V1 over T1 is equal to P2 V2 over T2. We're looking for V2, so I'm going to rearrange everything. And V1 over T1 times T2 divided by P2. Okay. Now that I have that, the combined gas law rewritten, now we can solve for our new volume. So P1 is 750 torr. V1 is 5.12 liters. T1 is 294.15 Kelvin. Remember, it's really important that when we work with gas laws, our temperature has to be in Kelvin, times T2, which is 298.15 Kelvin, divided by 1,429 torr. So we can see that my units cancel out, and I'll get something in liters. So it's 750 times 5.12 times 298.15 divided by 294.15, also divided by 1,429. Okay, so we get a volume of 2.72 liters. This is in three significant figures. Okay, that should be 3. Sorry for not putting a 0. So if you say, well, classically that should be 2, you would say 2.7 liters. And that would be my volume. Let's try another example. So another example would be something like this. Okay? All right, let's try this one. Okay, calculate density of sulfur hexafluoride. Gas at 715 torr. Okay, and 18 degrees Celsius. All right, so in this case, what's our equation to use? Well, we're asking for density. Okay, So if you have it memorized, that's great. Otherwise, we can rewrite it. So remember that density is equal to the molar mass, mu is molar mass, times P over RT. Okay, so basically, let's take a look. The molar mass, this is sulfur hexafluoride. So that's 32.07 grams per mole plus 6 times 19 grams per mole. So our units will be in grams per mole. Okay. And what we get is we get basically 32.07 times, not times, plus, let's see, 6 times 19 equals plus 32.07. Now we get the value 146.07 grams per mole. So now we have that value. The pressure is in torr. And in this case, because I'm using my ideal gas constant, we're going to actually have to convert torr to atmosphere. So to do that, we're going to take the 715 torr, and we know that it's 760 torr is 1 atmosphere. So what we get is 0.9408 atmospheres. Now this is going to be in 3 significant figures, but I'm not done yet. So I'm going to use the 4 and then pull it back to 3. Temperature. The temperature is in the Celsius, so we need to convert temperature to Kelvin. 18 plus 273.15. So we get 291.15 Kelvin. R is a constant and it's given. .0.08206 liter atmosphere per mole Kelvin. Okay, so now that we have all of our variables, we can now determine density. So let's go ahead and start plugging everything in. Density is equal to 146.07 grams per mole times 0.9408 atmospheres. All of this is divided by 0.08206 liter atmospheres per mole Kelvin. And all of that's divided by the 291.15 Kelvin. Okay, and we can see from our units, basically, the moles cancel out, the kelvins cancel out, and my atmospheres cancel out. So my units would be in grams per liter, which is exactly what we want for density of a gas. Okay, so you just say 146.07 times my 0.9408 divided by 0.08206 divided by 291.15, and what we get is our density is 5.75 grams per liter. Okay, so sulfur hexafluoride is extremely dense, and in fact, if you had an aquarium filled with sulfur hexafluoride, you could actually float objects on top of it, so it looks like it's actually floating in midair. Okay, all right, so let's take a pause here and move on to our next subject.